Hi, guys. Welcome back. We're on activity 13. I'm feeling really good. The activity that we are going to complete today is called Where Does the Light Go? So far in waves, especially the most recent activities, we looked at how light that was not transmitted through films, what happened to it. And so there's these, as waves carry energy, that energy can be absorbed, reflected, refracted, transmitted, kind of similar, and I'll show you some diagrams that will help you with that. So with this question, what kind of evidence would you convince you that this phenomenon was present? And it says record your answer. Obviously, I just want you to kind of think about it. If you'd love to record your answer, I would love for you to do that. Keeping your science notebook would be a really successful accomplishment during remote learning. So what happened to the light that was not transmitted through the films? And so we talked about that a little bit, but how would you prove that? How would you show to someone who's like, no, I don't believe you, I'm skeptical. And then you would say, well, wait, let me show you this evidence. When we had different films, we had 3 different films, and when we set them up in the phospho box, I know that the films absorbed the energy differently because the temperature in the phospho boxes changed at different rates. And therefore, I know that the energy that was absorbed the most increased the temperature the most. So that film would be good if I wanted to absorb energy and in turn turn it into heat. And so thinking again about the film on our car windows, we really don't want that to happen inside our car. So that choice would be a terrible choice to put that film on your car window because we want and so think about this. We want the energy from the sun to be reflected off our window, but if it's reflected too much, imagine driving around people whose windows are so reflective that it's like, it's too bright in my eyes. So there's this balance between safe driving and absorption and reflection of the material that we put not only on the windows, but also in the paint on the car, and those kind of things. So that's an interesting concept to think about when you're doing design. And with that balance of how do we think about absorption and reflection. So I do want you to kind of think about these. This is the copy of your electromagnetic spectrum. So here's my electromagnetic spectrum from last class, and I'll toggle back and forth between these. List the visible light spectrum from the longest wavelength to the shortest wavelength. What is the relationship between wavelength and frequency? Which wave transmits the most energy? And also think about possibly why. What do we know about the relationship between the characteristics of waves and how energy is transmitted? Activity 13, where does the light go? We are going to explore through our virtual lab how do different materials absorb or reflect light. In the previous activity, Selective Transmission, you learned that electromagnetic energy is selectively transmitted by some objects. This means that not all frequencies of light are transmitted through an object when the light hits the object's surface. Energy transmission depends on the combination of the wave's wavelength and the property of the material it hits. Look how I did that. Look how, as a experienced reader, especially an experienced reader in science, I predicted that when I saw depends on, I knew it was going to be scientific relationships. I knew it was going to be cause and effect. So my brain said, whoa. And then when I was reading, I slowed down and I emphasized. I would do that if I was sitting in this room by myself, which I am, reading this introduction. I would do that if I was literally just reading something and my brain go, oh, wait, this is important. So also another strategy is reread that. Energy transmission depends on the combination of the wave's wavelength and the properties of the materials it hits. Combination of two things. Interesting. Like other activities in this unit, you will use a model to gather evidence on whether electromagnetic energy can also be selectively absorbed and reflected. A model is a representation of a system or its components used to help one understand and communicate how the system works. So now we have selective transmission. Let's look. I re-emphasized a key to studying and remembering and putting information into long-term memory is repetition. You know that. Energy transmission depends on the combination of the wave's wavelength and the properties of the material it hits. Third time I've read that. Then I said, you know what? I need to put this in my own words and synthesize so that my brain can go, oh yeah, I don't like paragraphs. I like lists or bulleted or numbered so that I can graphically see that. There's a relationship between the amount of energy transmitted and combination, wavelength, medium. Our guiding question today, how do different materials absorb or reflect light? So in this activity, we are going to set up a little experiment. Our experiment for part A is on reflection. So we're going to separate reflection and absorption, and then we're going to kind of combine them and bring it back together. With this activity, you would get a plastic card holder. And on that plastic card holder, you would get your UV card. It's the same UV card we used in the last laboratory. That UV card, instead of facing the sun, is going to be facing down towards the black cloth, material number 1, and the aluminum foil, material number 2. And the reason it's facing down is because we are studying reflection. So I don't want to know what happens to the UV card when the sun's rays hits the UV card. I want to know what happens when the sun's energy, that UV energy, that UV wavelength frequency hits the black cloth and is reflected back towards the UV card. I want to know how the black cloth and the foil have different reflective properties. And obviously, intuition tells you, well, of course the foil is going to reflect. It's shiny. It also reflects light. The black cloth is a different material, and it may or may not act differently. Part A, we're going to watch this short video, and I'm going to go back and pretend that you didn't see that.
Answer the analysis items and give the completed student sheet to your teacher. Activity 13, where does the light go? Part A, reflection. Spread out the black cloth and the piece of wrinkled aluminum foil next to each other in the sunlight. The assembly is placed so that one side of the UV card is exposed only to the foil, while the other side is exposed only to the black.
So I didn't point that out in the setup, but look at how we've set this design up so that we can really tell the difference of where the reflection is coming from. And the other thing I didn't point out in the previous slide was that we crinkled the aluminum foil. So in your brain, think, why would we have crinkled it instead of laid it flat?
Cloth. It is exposed to sunlight for exactly 20 seconds. Compare both sides and record your observations.
So the way that the lab person on the video did this was the card is lined up evenly where this side was wood, the side that was being black cloth reflection, and this side was the side that was reflecting the energy from the sun from the foil side. So when you look at this card, what do you notice? This UV strip, remember from the last video, changes colors based on the amount of energy from that UV wavelength. And we know that the darker the color, the more energy there is. And you'll notice we talked about transitions a little bit too, but that plastic piece was right here in the middle. And this side had the aluminum and this side had the black. What do you notice? So the question really is, bringing back to our relationships between variables, cause and effect, those patterns in our data, what is the relationship between the material and the amount of reflection of the UV light? What do you notice with the material? And what's your evidence? I'm going to re-emphasize when someone asks you a question and you are going to make a claim based on something you've collected data about, you better include that evidence. If you're making a claim and you haven't collected data, that's called a hypothesis. That's not a claim. So here we've seen a little bit of data, right? Like it was a short experiment, but we have enough data to say, you know what, based on this experiment, here's what I think about reflection. For part B of this experiment, you're going to copy this data table down and we're going to fill out some information about temperature change. So now, in addition to reflection, another transmission feature is absorption. So our UV light can be absorbed, it can be reflected. Let's now go to absorption. With absorption, remember, really, how can I have evidence of absorption? Temperature change, easy. You still will have your black cloth, your aluminum foil, and then we will have a control. The first column will be your initial temperature. We are measuring in degrees Celsius. You'll have a final temperature and a change in temperature. So go ahead and pause the slide, the presentation so that you can record your data. Here's what the setup is going to look like. You're going to have a piece of black cloth. The black cloth is going to be folded over the bottom of the thermometer where the change in energy will stimulate the liquid in the thermometer. And the more energy, the more stimulation, the more those molecules move, the thermometer will read at a higher temperature. So we've got the black, the aluminum foil, and lo and behold, a thermometer just out, collecting data, information on UV light is just going to be the control. So I've got that open thermometer. So I shouldn't have showed you that. Going back to the video, you are going to come back and we're going to listen to part B. With part B, you have your data table that you've written down and you're recording this information into that data table.
Activity 13, where does the light go? Part B, absorption. Record the initial temperature on each thermometer. One thermometer is placed on black cloth, one is on foil, and the other is uncovered to serve as the control. All thermometers are exposed to sunlight for 5 minutes. Record the final temperature of each thermometer.
Did we get the initial temperature? All of a sudden I'm like, hey, wait, maybe I didn't rewind the tape, but I think I did, right? Did we get initial temperature? Make sure you've had a chance to record initial temperature. Now we'll get to see what the final temperatures were after 5 minutes of collecting data.
Serve as the control. All thermometers are exposed to sunlight for 5 minutes. Record the final temperature of each thermometer. Black cloth, foil, control.
Back to our data, you went ahead and recorded the initial temperatures, which were 21 for each of the conditions. So with this science experiment, we would have our independent variable would be the material. We would have 2 levels of our independent variable. We would have black cloth and aluminum foil, with our control just being no cloth at all. The initial temperature, so our independent variable, the type of material, our dependent variable, temperature change, really. The reason why we connect initial is so that when we collect final, we can look at the change. And it just so happens that the initial temperature for all three conditions were the same. That's rare, especially if we were in class in our science classroom. That probably wouldn't be the case. So we want to calculate what is the final changes of temperature for each of the conditions. Go ahead and do that and write that into your science notebook. Now that we have our data, and now that you have collected that change in temperature, what do you notice? Scientists collect data because we're looking for patterns, we're looking for correlations, we're looking for relationships, we're looking for, can we tell there's a cause and effect, or does it just look like there's a relationship where the patterns have similar patterns, where the patterns are similar, and so I'm not sure if one causes the other. You know, based on your science phenomenon and that science reasoning, that waves carry energy, that UV waves carry a lot of energy, that the frequency matters, and UV light has a higher frequency than even violet. And so, what is the relationship between the type of material and reflection? And what about the relationship between the type of material and absorption? So, looking at those conditions with the other two variables. So, we had an experiment that we were studying reflection. We had an experiment where we were studying absorption. Let's put this all together. With waves and energy being transmitted, here's three diagrams that kind of explain what's happening. With absorption, the wave hits the surface between a medium and another medium, and that energy gets taken in by the second medium. That is different than transmission. Transmission means that the energy coming from the first medium into the second medium just passes right through. Reflection, the first medium, the energy hits the surface and gets bounced off. Now, in the real world, you know that all three of these happen when UV light is traveling from the sun to the earth, to buildings, to cars, to you, to your skin, everything. When your cells are exposed to UV light, the absorption causes your melanin to increase its production and travel to your nucleus to protect your DNA. You guys, I mean, that's awesome. You're telling me that your body has a way to protect itself from UV harmful rays by giving you a tan? Now think of this. You live in an environment, excuse me, you live in an environment where it's super, super sunny all the time. You're equatorial, and that's super, super sunny all the time, and that equatorial zone is direct sunlight, and it's directly hitting your cells, and guess what? Humans that were born with higher amounts of melanin in their skin survived because they already had a way to protect their nucleus and their DNA. That is dark skin. Now, you know that there's also a relationship with the UV light and the production of vitamin D. And vitamin D is essential for our body functions and our enzyme functions. So that idea that there's this balance. I need some UV light. Too much, DNA damage. Too little, vitamin D deficiency. So thinking about that balance between absorption and reflection, if I have really light skin, I will get my vitamin D, but now I'm getting skin cancer. My melanin can't produce enough to take care of the DNA in my cells, and that happens where, through evolution, light-skinned people that lived in equatorial zones didn't pass on their genes to their offspring. They didn't live long enough to have offspring. Now, in places like Arctic areas, where the light is less intense, less directly shined on the earth, where the light is out less often, people with that dark melanin weren't getting enough vitamin D. Their skin was protected, their DNA was protected, but the amount of sunlight that they were getting wasn't able to stimulate that vitamin D development, and therefore they didn't live long enough to pass on offspring, genes to their offspring. Lighter skinned people were not getting skin cancer really because the direct sunlight wasn't that intense and they were getting enough vitamin D. So that idea that skin color and all these things we have about it literally is evolution and adaptation to different zones on our Earth's surface. It's really cool to think about it that way. So with these three, absorption, transmission, reflection, what was happening in our lab and in our experiments? I really liked this idea because with the previous slide, it makes it look like it could either be absorbed, transmitted, or reflected, but obviously it's a combination. So we know that not everything was absorbed. Some is absorbed, some is reflected, some is transmitted. And you'll notice refracted and transmitted could be together. So it might be transmitted through the second medium, but also bent, which would be refracted. So we've got these combinations of how energy and waves pass. And this is really important when you're thinking about designing cars, designing machinery, designing boats, designing sunglasses, designing ski equipment. One of the things you skiers know is snow is very reflective. And therefore, people, oh, it's winter, why do I need my sunglasses? Because you can go snowblind. That reflective light can actually damage your eyes so severely in the middle of winter in a snowstorm. Awesome. So here's a question I want you to think about. Which surface, the black cloth or the aluminum foil, reflected more ultraviolet light onto the UV card? And why or how do you know this? Here's a great diagram. This was in the chapter, the activity in your book. So that UV card was placed at a 45-degree angle. I don't think I mentioned that, but behind it was that plastic platform. So it was just set at a standard 45. That was one of our constant variables. That 45-degree angle with the UV card was facing down for both the aluminum foil and the black cloth. For these situations, the light hit the aluminum foil, and what happened to the light, the UV energy? Was it reflected? Was it absorbed? Was it transmitted? Was it a combination? Which of those terms would you use to say, here's really what happened the most? And then how about the black cloth? With these two diagrams that we just talked about, if the temperature, so now we think about building things and building materials, and again, that trade-off between I need reflection, but I can't have so much reflection that the people around me are going to go and get blinded because of there's so much reflection, but I can't have total absorption because then my car would be so hot, and you already know that cars get really hot, and how is the balance? And so this question is asking you more about roofs. And just, I think, the last voting cycle, maybe a year ago, one of the questions on the ballots for Denver was green roofs. So businesses that were building buildings had source, and I'm not going to remember exactly the law. So if someone in your house knows the law, great, talk to them and get the details. But it was something about with green roofs, what happens to reflection and absorption and transmission. Knowing that the color of my roof is going to matter. So in this question, according to the diagrams, which will the temperature increase more? If my house had a black roof or one with a shiny roof? In this activity, the black cloth modeled the dark ground. So when the sun is hitting the Earth's surface, when there is areas of darkness of the ground, what is going to happen to that UV light? Why do you think we used aluminum foil? We used the black cloth to represent. What substance could the aluminum foil have represented? And then I wanted to add this slide because this all relates to greenhouse gases. Many of you commented and appreciated me jutting in, information that isn't exactly in the chapter. And I appreciate that feedback, and it inspires me to find out cool information for you. So one of the things that makes our planet livable is we have an atmosphere. And that atmosphere keeps the surface of our planet decently warmed, consistently like a blanket, day, night, seasons. So something like the surface of the moon, there's no atmosphere for blanket. So during the day, the energy hitting the surface, it's super hot. And during the night, there's no energy hitting the surface. It decreases and dramatically drops in temperature. Well, the Earth is different. We have an atmosphere. We have this blanket of particles, of molecules covering in layers the surface of our Earth. And because of that, when the sun's energy hits, it does different things, including getting scattered. So of the energy that comes from the sun, 20% gets scattered and reflected to not heat up our surfaces. On a cloudy day, it feels cooler. 51% of the sun's energy is absorbed by the Earth's surface. Which part of the Earth absorbs the most? Land, water, liquid water. Liquid water, when you look from space, it's dark. Land, when you look from space, those rocks and the soil, dark. That 4% that gets reflected is really important. We can't absorb everything. Of that 51%, we get, what is happening to the absorption rate? And so we had this balance. We've had this balance in our Earth's history where the amount that got reflected was a perfect scenario to keep the homeostasis of the climate and of the Earth. Which surfaces on the Earth reflects? Well, a lot of it is the ice. And so what's happening with the ice is reflecting the sun's energy. Awesome, keeping me balanced. But as the ice melts, it becomes liquid. Liquid absorbs more, increases the amount of area of absorption. Absorption increases, decreases the amount of reflective surfaces. That makes warming. Reflective surfaces continue to decrease. The ice decreases, makes more water. Water is absorptive. That absorption, it heats up that surface, continues to decrease the reflective surfaces of ice. We call this a positive feedback loop, not positive because it's good, positive because something happens to make something happen more, to make something happen more, to make something happen more. And it's really this cycle, and it goes out of control. This is why your climate scientists are concerned about warming temperatures, because those warming temperatures have effects on how the materials on the Earth's surface act. If our Earth warms, where are we going to get our reflective surfaces from? So that's a really cool question for you in your generation to figure out. How are we going to get that energy reflected? Now, the other thing that happens as we get these layers on Earth and they get thicker and thicker and thicker, it's hard to get stuff out. And so we end up getting this increased thermal effect, which definitely AP Bio. I'm looking at you guys taking that class. So our question that we're going to finish with, how do different materials absorb or reflect light? My dogs continue to bark. I have no idea why or what they're barking at. So I'll leave you with that, and I'll talk to you soon. Bye.